This video is about drawing cross sections. So this is something that you'd experience in Year 12 Earth and Environmental Science, and it's the geology component of that unit. Let's have a look. Before you start this, what I want you to do is I want you to download this document, and if you click on that link, it's in the description. Right, it'll take you to Google Drive, and if you have the link, you've got access to that folder. So that's what I want you to download and print in order to make this a bit easier. The last option is not going to work. You could try, but what it would mean is would mean that you'd need to draw your line with the same measurements as whatever your screen is. So if you're watching on a phone or something like that, it's going to be too small. Yeah, so it's a bit of a challenge. You could make it twice as big, but then you're going to get a ruler and you're going to have to measure on the screen and stuff like that. Anyway, if you want to try that, good luck. What we have here is a geological map. So it's from above. They've kind of put it at an angle to make it a bit easier to see. We've got A and A prime, or A dash, doesn't matter what you call it. They've given you the topographic profile here. That's not always going to happen. There's no information in this diagram above, or in this map above, to get you to this point, so it's been given. So we have both of them strike north-south, so that's nice and convenient. But each of them have a dip, but they're in opposite directions. This one's dipping to the west and this one's dipping to the east. So I've got the profile here. What they've done is, first of all, they're taking the width of each of these sedimentary layers. So this Silurian sandstone is this one here. And then we have this one here it's the blue one, it's the Ordovician limestone. Then in the middle we have the Ordovician sandstone, limestone, sandstone again, and then there's shale on either end. So the first thing you do is you get your protractor out and you lie it sort of like the flat end there and the round ends down here. And you put the crosshair of the protractor on that, right on that spot there, and then you see where, because we've got a 45 here on that bed, so we see where 45 is and we draw lines. Now I wouldn't necessarily do lines that are that long. I would do them a little bit shorter. You don't just draw them and keep going like that. And so we got the other side as well. We got the middle here. So what we can see here is then they've drawn layers. Now they've just assumed that nothing changes. And we don't really have much information. All that we do know is that's going to be a fold coming out like that. That's all we know. We don't know what's going on to the east or the west of this thing. Okay? But yeah, don't do long lines, and you will see why shortly. Here's another one. We've got an unconformity here that looks like a metamorphic rock maybe. If they were granites, they'd be plus signs. So we've got A to A prime again, but we've just got the above view here. So we've got, these ones are all striking, we don't have a north, we do have a north. So these are all striking north-south. So again, that's nice and convenient for us. So these are all 20 degrees. So you put your protractor on and we look, see 20 is quite shallow, 0 is flat, 9 is straight down. So we can see the 75 really steep. This one's a 60, so that's unusual. They're just assuming uniform thickness and continually going at the same angle. And then we don't know what rock types these two are. There's nothing at the surface that indicates that. Here we've got another one. So this is what we would see. This is our geological map. So we've got sandstones exposed. Oh, I'm assuming it's sandstone. Yep, sandstone's exposed at the top. Is that that's a limestone, and that's a shale. So the purple is shale. And what we get from this one, this is a bit more interesting because we got dipping that way and then dipping that way. So they're dipping towards each other and then away from each other. So we know we've got some folding going on. So our dip's at 30 here, our dip's at 76, it's a bit steeper, and then our dip's at 40 through here. So we've got a fold to one end. It's not this perfect last one. So that's a 3D one. You're probably not going to be asked, or you're almost certainly not going to be asked to draw one, but you might be given one and have some questions on it. This one's, we can see that the strike and dip is changing in this one, and they're all going away from a center point. What this tells us, and you're probably not going to get a question about something like this, but it's pretty cool. It's called a dome fold. So it does. It's kind of like, it's got that fold, but then if you turn it around 360 degrees, wherever you look at this, it's the same. So it's kind of like a hill, and then it is folding as well. That's just something that's interesting. We're going to do a worked example. These are plunging folds. We can see that they're not neat. So they're kind of, the anticlines are kind of like, so it's folding this way, and then they're also plunging into the ground, which is why they're not completely exposed. So a few different rock bodies here, some Silurian and some Ordovician rocks. We got a transect which is just being called XY. We have some strike and dips. They're all approximately, where's our north? We can just assume north is in the upwards direction. I think if you don't have a clear indication, just do that. They're all approximately going, so northeast, southwest in their strikes. And these are dipping towards each other. These are dipping away from each other. We just assume that it's uniform through all of the beds, unless you're given more information than that. We've got a fault here, but lucky for us, it's not on our transect. They've given us the cross section in this example, and let's do it. So first thing you're going to do is you're going to confirm that the transect and the width of your actual thing, so this transect is the same length as this one. If it's not, you're going to find yourself in trouble. So if that's 15 centimeters long, that needs to be 15 centimeters long as well. So just quickly check that, because sometimes if someone's printed it out for you, it's unlikely that would happen in an exam, but it could very well happen in a test. Make sure they're the same, and then what you want to do is you want to look at these thicknesses of different layers. Confirm the scale on the map is the same as the cross section. So we can see this first one's about 1.1 centimeters. So here we go, 1.1 centimeters. Then what you want to do is all of them, all of the layers, all the way across. And then you want to make it so, just ignore that little one there, ignore that diagonal line. So then you want to transfer them up onto the actual topographical line. So we got them all up here, because that is where your dips and strikes are measured from, not down here, not at sea level or not at wherever under the ground. They're done up here. I would suggest doing your markings across the bottom, then transferring them up. If you try to do it up at the top, I don't know, I think you might get yourself into a little bit of trouble. Identifying strike and dip directions at different layers. So looking at up here, so it's at 35. Just going to assume that the one next to it is 35 as well. You get your protractor, you put the cross area protractor right on that first spot. And then you look at 35, which is here, and then you do a dot right there. Then what you do is you line it with the dot and your marker, and you do a little line. Don't do a big one, just do a little one. Because if you do a really long one, it's going to interfere with what you're trying to do later on. Might not cause you any problems, but quite often it stops your folds being, assuming there's a fold, stops your folds being nice and smooth. I know they're folds, I've done it already. So you do it for all of the points, and you've really only got those 4. So let's have a look at it. We've only got 1, 2, 3, 4. Then what I would do is I would rub out all these ones along the bottom, just to clean it up, get them out of the way. And then what you want to do is you want to do beautiful, nice lines, making sure you're hitting the same layer. So you're going to make sure this one hits that one, but this one hits that one. Otherwise you're going to get your layers all mixed up. Alright, so that's determined the same spot. And then you do your nice folds. We notice how they're at slightly different angles. So one's going a little bit deeper than others. You can extrapolate it out by putting a dashed line above. Be really careful over here, because we don't actually know where that fold could be right there. Unlikely that it's going to be right there, but it could be. So you don't want to extrapolate that direction. I started doing it and thought, no, can't do that. And then I added colours that corresponded with the initial map. Now, I can't take for granted how thick that layer is. So I've only just drawn the start. If you come in and you just go blah, blah, let's have a look at the original. We don't really know. Look at that. We don't know how thick these layers are. Not really. So the shales, we don't know how thick they are. So probably you'd be telling a bit of a fib if you tried to make them fully thick. So I'd just leave it like that if you're colouring. Okay. And that's what it looks like across the Transics. So we can see the bit of red in the middle and then the green either side. That's orange. But I've done that for the brown. I thought it looked orange. And then the yellow and then the purple one. This one's here. I was going to do this one as well, but it was going to take me too much time. So we got some WACE questions now. So we have one here. Use this map to answer the following questions. So you've got to start by constructing the cross section. We can see that we have some topographical stuff. So you have to draw that first. Got our scale at the side. Biggest one is 600 and they're telling us to start at 300. So 4, 5, 600. Then what I would do, well, you've got to do the topographical line. So you're looking at these exact points. This is one you might mess up there, because the other ones are close to the line, but that one's kind of up there on its own. So you put those points down. That's approximate that I've done. You can probably be more accurate than that. And you just assume that it's the same height going across of the same bedding layer. There's nothing else you can do with that. If you don't assume it, you've got nothing to work with, so you've got to go there. We've got a couple of strikes and dips. We've got a 60 and a 45. But anyway, so we've got our points. Then what we're going to do is we're going to do a line. So the topographical map is something like that. That's pretty close to what it is. Then I put the dike in next, so this dolerite dike. So we'll chuck that in. And then what we want to do is we want to put our strike and dips in. So they're all striking perpendicular too. So it actually doesn't matter even if they're going at an angle. When you do the cross section, it's going to look like it. So it's a bit of an issue actually when you've got an exposed rock face. You can't assume that it's coming straight out. So you can't assume that it's flat. It could be coming in on this big angle, kind of like this dike. The whole thing could be like that, but from the surface it just looks like a rectangle, looks flat. So you need to look at other indicators to determine that. But anyway, up on the bedding up here we can see that. So we've got these ones here and approximate thicknesses of the layers in there. We've got this, the 45 is up there. Now, we don't have any information about this granite intrusion. So what we need to assume is it's just going straight up and down. You're not going to be able to, it doesn't have bedding in it. So you're really not going to know unless you drill cores or something like that. I think it's pretty tricky for you guys, if you saw this question, to identify that. I know it because I've seen the answer, but you may not. Alrighty. One of the tricks to this one is these layers don't exist in this cross section because it doesn't cut through the conglomerate, the shelly limestone or the mudstone. So they are not included. That's a red herring. You might fall for that. You might try to draw them in, but look where the transect goes. And we can't make assumptions what happens below this. This is a granite as well, which means it's cooled under the ground, so it kind of flowed out and flowed over the top of it all. It has to be granite below it. Make sense? All right, so that's what you should have come up with. Something looking like that. There's a metallic ore deposited at the surface of the area adjacent to the granite, so next to the granite, at the boundary between the sandstone and the shale. So next to the granite at the boundary between sandstone and shale. So what we need to do, we need to identify a point below the surface at which mineralization might occur, mark an X on the map. So we can see that the sandstone and the shale are here, and the granite's there. So where they intersect, next to the granite. So that's our spot right there. We need to transfer it to our map. So that's it. They want you to do it on the actual map, not on your cross section. So you're using your cross-section to identify it. Now you're going to get this mark even if your cross-section is a little bit out, so long as you identify that spot. At what depth below the surface would your planned hole be expected to encounter the mineralized zone? So maybe 520 there, down to about 420, so you know, maybe 100 meters. And again, if your diagram is off, but you get the distance, just say on your diagram it's 150, they'll give it to you. Okay, so persevere. So an appropriate type of name for the metamorphism, the zone around the granite. So because it's in contact, it's contact metamorphism. This is not regional metamorphism. Two textural differences. So there's an alteration zone around it. These are all sedimentary rocks. So they don't have large crystals in them, do they? What you're going to get is you're going to get a reasonably high grade, high temperature, probably high grade metamorphism around here. So you're probably going to get something that looks like gneiss, or even a mica schist or something like that. So you're going to have interlocking crystals, and you're going to have larger crystals, because it's just a comparison between that and the surrounding sediments. Surrounding sediments would have small or no crystals, so the shale's not going to have anything. So here's another question. We have our geological map. We've got some different layers. They're all sedimentary, though we have garnet schist, so we've got a metamorphic zone there. The rest of it is sedimentary. So there's a basalt dike cropping out at point X. It's visible at point X. The dike's approximately 50 metres wide, strikes east-west, intrudes vertically into the country rock, so it goes straight 90 degrees. It's got a dip of 90 degrees, and it's older than the mudstone but younger than the limestone. So it's younger than limestone, so it'll be on top of the limestone, or it'll cut through the limestone. And it's older than the mudstone, so the mudstone would have been deposited on top of it. So add the dike as a feature. So cropping out at X, it's east-west and 50 metres wide. So that's 200 metres. That's 100, so 50 is about that, so you're going to make it about that wide. Going east-west. Let's have a look. Now for me it says cropping out at X. Ooh, which kind of gives me an idea that it just starts at X, but they've made it go the whole way across. I reckon if you just do it half, you should get given it if you do that, but anyway. But we can see that it doesn't cut, it cuts the limestone, but it doesn't cut the mudstone. It's underneath it. Metamorphism of the schist in the northwest of the map area would require temperatures and pressures corresponding to blah 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 burial beneath the surface. But what's sitting on top is unmetamorphosed. So the schist is the stripy one, and it's got limestone on top of it. So the schist and the limestone are sitting on top of it. What's a geological history required for that to happen? So for schist to be underneath limestone, so we've got an unconformity there. What's happened is that the schist is formed deep below the earth, and then it's uplifted somehow, and then it's weathered and eroded off the top. Then sea levels come in. It doesn't have to have been too deep for limestone, so there must have been a coral reef form on top of it. So now you need to do the cross section. They've given you the topography. How convenient that is, perfectly straight. So I've gone A prime to A. Make sure you get it the right way around. Usually it's A to A prime. They've been a bit cheeky in this question. I don't think they should be trying so hard to trick people, but anyway. I want you to attempt this yourself. Again, I haven't done this, but I do have the answer. See how you go. So we have one dip of 40. So pretty much everything's dipping at 45 along the same line as the transect. There's a bit of a hint for you. And you need to make sure you include the dike, the basalt. Let's have a look. So this is what it looks like. So they're at 45, the dike comes through, and then we have stuff deposited on top. We know these are 45, this was vertical into the ground, and then that was deposited on top. So we can see that we got these formations all have 45, or these layers all have 45, but there's nothing here. That's pretty hard for you guys. So don't feel too bad if you've tried to do 5 and 6 at an angle as well. Just remember, if that's vertical into the ground, it's got a 90 degree. So the movement has stopped. Whatever folded the rest of the rock didn't happen anymore. Now if this dike wasn't at 90 degrees straight into the ground, that would make it a lot trickier, wouldn't it? But it's at 90 degrees and it's older than this layer. Must have deposited flat on top. Changing lithological character of units 2, 3 and 4. 2, 3 and 4. So shelly limestone, marine sandstone, terrestrial conglomerate indicate the variation in local conditions. Well, could be limestone, sandstone, conglomerate, sea level change, couldn't it? That could be the variation in local conditions. That's the easiest one. You could talk about a temperature change, and the terrestrial conglomerate could have come from a glacier. It could have been too cold for the corals to continue to grow, and then the sandstone could have deposited on top of it. But your best answer is sea level, change in sea level. So we got topographical stuff. We got a distance, and we got the strike's going perpendicular again to the transect, which is good, and the dip's going parallel, pretty much parallel to the transect. We have this spot X here. So I need to produce the cross section for this one again. So do that now. Make sure you do the topographical line first, and then you put your strikes, or you put your dips in for particular layers, and the conglomerate doesn't appear to have a dip on it. What about the basalt? Nope, the basalt doesn't have a dip. The siltstone doesn't have a dip. Do your best. Okay, how is this transferred? So you should have got that topographical line pretty well. We can see that these do not have the dips. Okay, so they're all flat. This one has a dip though, doesn't it? 60. If you did that straight, you could be forgiven, but we can see it's part of a fold. This is tricky, guys. Don't be too hard on yourself if you're not seeing this. So long as you're understanding it once you see it, and so long as you're having a go at it without looking at it, you're going to improve. Okay, so the sandstone is coming. So we've got the dip at 30, so it's far shallower and it's far steeper there. Then we have underneath, we've got the mudstone. We're not sure about that, but we do know that this dike right there, so the andesite dike. Hopefully you got something that looks like that. I've just been going through and editing this video, and I've spotted something that I think it's a mistake. I don't really like it. So what it is we see here, and we're looking at the limestone. Now it says the limestone has a dip of 60. But if we come back and we look at it here, there's no dip in that limestone. The sandstone's got it, but the limestone doesn't. What really should have been drawn, well, who knows? This is unknown rock. We can't say that's limestone over there. Anyway, I just noticed that, so maybe you noticed it too, that the limestone's got a dip, but then in the actual answer, the limestone doesn't have a dip. Drill a 250 metre deep hole at point X. So we've got point X. Start in the conglomerate, list in order the next 3 lithologies. So X is really close to A, so probably somewhere here, and we go straight down. 3 lithologies you'd find. So you're going to start with the conglomerate, the next 3, so we don't count the conglomerate. We go with the basalt, then we go with the siltstone, then we go with the limestone. What is the oldest lithology in this region? So sandstone is underneath that, so that folding has happened before the limestone has appeared. So that's older than that. And this mudstone is sitting underneath the sandstone. That's cross-cutting the mudstone, so that must be younger. So the oldest has to be the mudstone. Geologists who produced this map was not sure whether the basalt encountered in the northwest was intrusive, was a sill, or a flow. So whether it flowed out over the top of everything, extrusive flow, or whether it was an intrusive sill. So it was a sill that split off from a dike and went in between layers. Two pieces of evidence you'd look at. So this is the basalt. If it's a sill, you're going to have metamorphism above and below because of the heat. If it's an extrusive flow, you're going to notice that there's a weathered or eroded layer here on top of the basalt, and then so it's uneven, and then the conglomerate was deposited on top, so you're going to notice something about that top. But also, if it's a flow, you're going to have metamorphism underneath, so these siltstones are going to be metamorphosed right on the top, but the conglomerate's going to have no metamorphism in it. So that would be another indicator. Does that make sense? I hope so. Anyway, hope that went well.